Okay, so here's our third and last topic in topic 11, all about capacitance. So let's go. Number one's pretty straightforward. It just uses the equation for capacitance. Okay, 2 through 5. 2 and 3 are for a parallel circuit. 4 and 5 are for a series circuit. In parallel, capacitors add up. In series, they do the reciprocal, like with resistance in a parallel circuit. So for number 2, 3 identical capacitors of 725 microfarads. That's 2.18 times 10 to the negative 3 farads. Number 3, the charge on each of them. I know the capacitance, and they're in parallel, so it's the same as the total. So C is Q over V, solve for Q. It's actually the same numbers as number 1, 2.36 times 10 to the negative 3 coulombs. Then number 4 is in series, so equivalent capacitance. We use the reciprocal equation, we wind up with 2.42 times 10 to the negative 4 farads. And then for number 5, the voltage on each, it's a series circuit, so the voltage is distributed. 3.25 divided by 3 is 1.8 volts on each capacitor. Okay, so 6, we have a 725 microfarad capacitor. I love that number, I guess why not? And we have a dielectric in there with a permittivity of 4.5 E naught, and the plates with a diameter of 0.75 centimeters. Really? That's a very small plate. Oh, I guess, yeah, that's true. It's a small circuit element. Anyway, so using that diameter, I figured out the radius. I do pi r squared to get the area. I'm going to need it because capacitance is emissivity of the dielectric times the area over the distance between the plates. So solving for distance between the plates, when you throw all the numbers together, you have 4.5 times the emissivity of that E naught number. Yeah, not permittivity, emissivity, or emittivity, whatever, you know what I'm talking about, the E naught number. It's in the constants. 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. And then I put in the area that we calculated and the capacitance in farads. And when you work those numbers out, you get 2.43 times 10 to the negative 12 meters as a separation between the two plates. So yeah, 2.43 times 10 to the negative 12 meters is 0.002 nanometers. Visible light is in the like hundreds of nanometers. So that is way too close. So yeah, like this larger capacitor could be constructed using parallel plate architecture. No, they're way too close together. Like you're not, I don't even think that's like possible. I think just by like molecular interaction, they would just jump towards each other. Anyway, that's number 7. Let's move on. So number 8 is pretty straightforward. It is, they give you the capacitance and the voltage, and with the energy, 1/2 CV squared. That's it. Don't forget to square the voltage. Okay, number 9, we have 3.25 volts on C1. C1 is 125 picofarads. Pico is 10 to the negative 12. And so if C is Q over V, Q is CV. I'll multiply them up. 4.06 times 10 to the negative 10 coulombs. Then it says the switch is closed connecting C1 to C2. What's the new charge on the plates of C1? So this is a series loop when you close the circuit, and so they would share the available voltage, but they would have the same charge on each because they have the same current, because they're in series with each other. And so the originally C2 was not charged, and so then that all of the charge that was on C1 is now split between the two, giving 2.03 times 10 to the negative 10 coulombs on each capacitor. If you actually look at the Lund notes that this question is based off of, Lund's analysis says that the two capacitors are in parallel. I would not call that parallel. That is a single loop, a single connection. That is the defining characteristic of a series circuit. And if it's a series circuit, they're going to have the same current in both of them. Okay, 11. So let's see, I bet they want curves for the capacitors, or they want it for the resistor. No, it's a different setup. They just want 11 is just, yeah, 12 through 15 is different. So they just want the curves for the capacitor. I'll also include the curves for the resistor. I've been banging my head against the desk for like the last 10 minutes to figure out what the heck he's talking about when he says RC increases. To show how the curve itself changes as RC changes. So if you had like a high value resistor and a high value capacitor, but the resistance and the capacitance of the circuit elements themselves stay constant as the voltage is applied. The voltage will change and the charge will change and the current will change, but C and R stay constant. So, voltage graph. All right, so this is the voltage graph for across the capacitor if you have a low resistance, like low resistance or low capacitance, or really just the product of resistance times capacitance is a low value. Now let's remember that R is V over I, so resistance is proportional to voltage. Larger, like smaller resistors have less of a potential drop across them. And C is Q over V, so for the same charge, C and V are inversely proportional. So for a low value of C, that's going to be a higher value of V, because C and V are inversely proportional. So if R is low, or if C is low, that's going to be a higher voltage across the capacitor. Let me go back to the R equals V over I. When I say R is V over I, a lower resistance across the resistor, so R of resistor is low, then V across the resistor is low. And since the resistor and the capacitor are in series with each other, that means the voltage across the resistor is low, the voltage across the capacitor is therefore high, because the resistor and the capacitor share the available voltage. So if the resistance value is low and or the capacitance value is low on a capacitor, then that's the maximum value across the capacitor. Now, if your resistor value is a high resistance and or your capacitor is a high capacitance, then that's going to be a minimum voltage across the capacitor. So that curve would look like this. There would be less voltage across the capacitor. If you had a high value resistor, it would take more of the share of the voltage, leaving less of the share of the voltage for the capacitor. Also, if your capacitance were high, since C equals Q over V, if C increases, then the voltage across the capacitor for the same level of charge decreases. So for both of those reasons, a high RC is going to be minimum voltage across the capacitor. Also, notice the way I drew the curve. The actual time to charge the capacitor increases as well for two reasons. A big resistance means a slower or less current, so that the current's going to be slower, giving less charge to that capacitor over time. Also, a big capacitance, that says big. Big capacitance means a bigger charge bucket to fill, so there's less current, so the charge is slower, and it's a bigger bucket, so it takes longer. That also means for a low RC, it's going to take less time. And then, of course, if you have a medium value, it's going to be in the middle, following the same logic. Now, that's the voltage across the capacitor. The voltage across the resistor is going to be the inverse of that. And it's because the voltage is shared. So whatever the voltage is happening across the capacitor, the inverse is happening across the resistor. These are charging curves. Okay, 12 through 15, we have a loop that includes a resistor and a capacitor and a switch. One side of the switch is connected to a power supply. The other side of the switch is just, it disconnects the power supply and it just includes the capacitor and the resistor. So in the current position where the capacitor and the resistor are connected to the power supply, that's the charging condition. You said to label that with A, that connects it to the battery, and then if you wanted to discharge the capacitor, you disconnect the circuit from the battery, so then the capacitor is able to release its voltage, discharge, and that would be the B position. And then 14 says draw the direction of current flow during discharge. First, we have to establish the signage of the capacitor. We know that this cell right here, we have positive terminal up here on the top. We have negative terminal down here on the bottom. So in the charging condition, the positive side of the capacitor is up here on the top because it's connected to the positive terminal. And then down on the bottom, we have the negative terminal. And then if we then close the switch for discharge, so if I move that switch to the discharge position, I can see that the top plate is positive and the bottom plate is negative. So in the discharge condition, we're going to have the current flowing this way through the loop, coming back this way. Okay, so 15, Kirchhoff's rule for voltage means that the sum of the voltages is going to be 0. That the sum of the sources is plus the sum of the drops will be 0. And so the source in the case of the discharge is going to be the capacitor, and then the load or the drop is going to be the resistor. And so the voltage across the capacitor equals negative the voltage across the resistor. Voltage across the capacitor, if C is Q over V, then V is Q over C. I didn't write that. That's C is Q over V. Therefore, V is Q over C. That's where the Q over C is coming from, where C is the capacitance. And then, of course, V is IR, so the voltage across the resistor is IR. And I, current, of course, is change in Q over change in T. So we wind up with Q over C for the capacitor is equal to negative the current, negative the rate of change of current, times the resistance value. Okay, let's continue. It looks like numbers 16 through 21 are based on that description. 725 microfarad capacitor charged to 2.35 volts, discharged through a 15 million ohm mega ohm resistor. Find the time constant tau. And so we have 15 times 10 to the 6 ohms, and we have 725 times 10 to the negative 6 farads, and that gets us a time constant of 1.09 times 10 to the 4 seconds. That's about 3 hours. And then we're looking for the initial charge on the plates, or the Q that was on the charged capacitor. So C is Q over V. So we get 1.7 times 10 to the negative 3 coulombs, or maybe 170 microcoulombs for the charge on the plates. Find the charge exactly 3 time constants after the discharge has begun. So the charge after time is given by initial charge times e to the negative time over tau, and the time is 3 time constants. So then I plug in the numbers, of course, 3 time constants. If you basically you're saying e to the negative 3, 3.27 times 10 to the 4 divided by 1.09 times 10 to the 4 is just 3. So that's 1.7 times 10 to the negative 3, and we wind up with 8.46 times 10 to the negative 5 coulombs. So now going from 170 microcoulombs to 84.6 microcoulombs. Sorry, 1700 microcoulombs. All right, capacitor's voltage, 1870 seconds after discharge begins. There's the formula for voltage. V naught was 2.35 volts. We wind up with 1.98 volts. Instantaneous current at 1870 seconds. Okay, so for number 20, to find the instantaneous current at 1870 seconds, we actually have to reach back to number 15. we had that Q over C is negative delta Q over T, or delta Q over delta T times R. And so if we rewrite that for current, we get current is negative Q over RC. We know that RC is equal to tau, or the time constant, so the current at an instant in time is the charge, negative the charge, over the time constant. So we're going to use that, but first we need to find the charge at 1870 seconds. Now you might be interested to say like, oh, well, the current is actually equal to the initial current times e to the negative t over tau, except the initial current, when we first began, we don't actually know, so we can't use that equation. So we find out that the charge after 1870 seconds is 1.432, etc., times 10 to the negative 3 coulombs. If I put that into instantaneous current is equal to negative that over tau, I get that the instantaneous current there is 1.31 times 10 to the negative 7 amps. All right, half-life of the capacitor's voltage. So I want to find the time when voltage is half what it was originally. So I'm trying to solve for time here, so I'm getting e to the negative t over tau alone, and then what I'm going to do is I'm going to take the natural log of both sides to get rid of the e. So I took that natural log, I get negative t over tau equals natural log of v over v naught. And so I multiply both sides by tau and negate both sides to get t by itself. So the time, the half-life, is negative tau natural log voltage over v naught. So I plug my numbers in, and there's my half-life, 7.555 seconds, or 7, let me write it in scientific notation, 7.56 times 10 to the 3 seconds. Another formula that they have in the Lund notes, which is much cleaner, is that the half-life is the time constant tau times the natural log of 2. That's a much nicer way of getting it. So if you do 1.09 times 10 to the 4 times the natural log of 2, you get 7,555. All right, we're almost done. There are 3 more questions on this worksheet capacitance situation. All right, we have a timer, RC timer, and it needs to have a half-life of 60 seconds. They have the initial capacitor charge and the initial voltage. What should the value of the time constant be? Hey, let's use that handy-dandy formula that I just wrote down. The half-life is the time constant times the natural log of 2, therefore the time constant is the half-life divided by the natural log of 2. And we get a time constant of 86.6 seconds. What value should the resistor have? Hey, the time constant equals RC. So that 86.6 is actually 86.5617, etc., but I divide by the capacitance and I get 119,395, so that's 1.19 times 10 to the 5 ohms for the resistor. And then what is the voltage at that time? At the time of 60 seconds, I guess, at the half-life. So we can get that with V is V naught e to the negative t over tau, and capacitor voltage. Yeah, the capacitor is initially 6.25 volts. So we do 6.25 times e to the negative 60 over 86.6, and we get 3.12 volts for the voltage at that time. Okay, terrific. And that was the last question for the Mr. G on 11.3 capacitance. Did that under 20 minutes. Cool. Thank you.